All right, let's discuss how we tokenize audio here. Okay, so audio files, right? So these are inputs. In the example we shared over email, something like Nori voice .wav. So these are simply wave file, right? So we have something like wave. Let's say we have 2 seconds, and the sample rate is 16K. Now in this case, this wave is represented as channel size, and then the number of the time steps, which is 2 seconds, so 32K, right? 16 times 2. So these are continuous values. So in our case, C is actually one channel. But in applications like music, we have multi-channel stereo generation. So C could be something like 6, right? So we have this 1 by 32K dimensional vector, and each entry is floating numbers, something like this. Now, nobody really wants to work with this, right? Because it's just huge. It's a floating number, 32K for 2 seconds. It's huge. So we want to downsample or compress it. So that's what we call encoding. Or in this case, equivalent to pretty much tokenization. Then after we tokenize, we generate in the same way, we generate tokens, and then we detokenize the tokens to get the final WAV file, right? So that process is called decoding, and which is equivalent to detokenization in our case. Okay. And tokenization is something like words, right? So this reminds us of words in LLMs. So LLMs text is basically tokenized into tokens or similar to words, or actually subwords. We actually further separate words typically. But anyways, so and then they are basically just discrete tokens, so they can be represented as integers. The vocab size is something like your dictionary, how many subwords you have. In natural language processing LLMs, we typically have vocab size, in the case of like llama, 32K. This is, however, this is the number of number of words in your dictionary, right? But in the case of audio, actually, we have typically 1024. We'll discuss this later, but 1024. But the sequence is usually much longer than word or text input. Okay. All right, so how does this encoding work? So encoding works. So this dense vector is fed into convolutional neural net, right? So layers of convolutional neural nets, similar to, for example, when we do image classification on images using like ImageNet data or something like that, right? So you have convolutions, you have pixels, right? So you have pixels by many pixels as a square or a rectangle, and then you downsample it to get a dense vector, right? You compress it in a dense vector using layers of convolutional neural nets, and at the end you do image classification, like is this image cat or dog or something like this. So we do this similarly for audio. So convolutional neural network, layers of convolutional neural networks, right? And then we get D by T dimensional vector, or the matrix, right? D by T. And the T is the time step. So this is usually much smaller than 32K. Let's say T is 256. So much smaller than 32K. And D is conventionally something like 1024. Okay. All right, so that's the matrix. And these are continuous values. So these are floating numbers. Okay. Now, but we need to do tokenization. So we need to discretize them. So how do we discretize this? So let's slice one time step. T equals 1 here. Let me use red. Okay. Let's say this is 0.3, 0.5, blah, blah. Okay. So 1024 of these, right? So this is a 1024 dimensional vector, and we represent it as a sequence of tokens. So this vector, let's call this vector, let's call this vector H. Okay. Vector H. So we represent H as sequence of integers. How do we do this? So here we actually we introduced the concept codebooks. So we have let's say we have 10 codebooks. Okay, codebook 1 up to codebook 10. So it's a book. So we have vocab size vectors inside. So again, the vocab size in typical audio tokenization is 1024. So you have 1024 different vectors in the codebook. It's kind of like a lookup table. It's a book, right? And because these 1024, it's just actually turns out to be square the 1024 vectors. So these are separate vectors. So let's call this V1, because this is codebook 1, superscript 1, up to V10, superscript 1. And then, okay, so that's a set of vectors, sequence of vectors. We have 1024 of these. Okay. Actually, sorry, 1024. And we take similarity between H. This is the vector we want to represent. Right? Similarity between H and these vectors. So V, codebook 1, and I, and of course I goes to goes from 1 to 1024. And we take the biggest similarity vector, right? So let's say we ended up getting V11 as the closest vector. Similarity could be measured as like cosine similarity between vectors. So V11, we ended up choosing I equals 1, that's closest to H. Right? So we get V11 as the closest one. And then we do the same thing for codebook 2. But now, instead of taking similarity between the original H and let's say this is codebook 2, so V superscript 2, 1 up to V1024 superscript 2, we don't take the similarity between H and these vectors. We actually take the residual, right? So we're getting closer to the original vector H. So H minus V, so 1, 1. 1 is the first integer, or the first entry we ended up choosing, right? The closest possible vector from the 1024 vectors from the codebook. So this is R1. And now we do the same thing, R1 and VI superscript 2, because it's codebook 2, right? And then we choose the closest possible vector. So let's say we ended up choosing I equals 10, okay? And then we keep doing this up to codebook 10. So first codebook, we got 1. And second book codebook, we got 10. And then the last codebook, we might get codebook 2. So this is a sequence of 10 integers. And if we add these vectors, like corresponding vectors, it gets closer and closer to the original H. So in this case, we are approximating, discretizing the original H using a sequence of discretized vectors, or discretized integers, getting closer and closer. As we get more and more codebooks, we get closer and closer. But of course, if we get more codebooks, the information gets bigger and bigger, and the compression rate is getting smaller and smaller. So it's a trade-off between accuracy and the and compression efficiency. Okay. Right. Let me erase this. Okay. So now we have 10 codebooks, and each of these consists of 1024 lookup vectors, and we choose the closest possible vector, and then add them all up, right? So it gets closer to the H vector we have after the convolution neural networks, right? So now we can represent this slice from the compressed vector by a sequence of vectors, or a sequence of integers. Okay. So in the case we had before, 1, 3, 10, I don't know, it could be whatever, 5, right? So this corresponds to V1 codebook 1, V3 codebook 2, and then V5 codebook 10, 10, right? Okay. Okay. So we do this for each of these slices. So we get, this will be approximated by integer matrix, and D will be number of codebooks, right? 10. So number of codebooks can be called NQ by T. We do this for all the time steps, right? And then each time step, in this case, 1, 3, 10, up to 5 or something like that. And then you have integer matrix, right? Now this looks a lot like word input. These tokens are kind of like words, except that this is actually two-dimensional matrix. It's not like sequence. It's actually matrix, right? It's not a vector, but it's a matrix. But then they are vectors now, or they are integers, right? So okay, so we can input this integer matrix into a transformer. You can flatten it or whatever. We can do whatever, and then take the transformer takes as input the sequence or the integer matrix. And then we can do similar left to right autoregressive training. So this can be used for generation, right? So the generation task is to generate these sequence of tokens or sequence of integers, right? So we generate this integer matrix from the transformer. Okay, so that's great. But then at the end, we want audio output, right? So this is still in the discretized world, and this is not audio. So we have to do the opposite, the reverse process, which we call detokenization or decoding. Okay, so detokenization takes as input this kind of matrix, right, and then reconstruct the original, reconstruct the WAV file. Again, we use convolutional neural network. And then do something like we get the panel size by 32K in this case, right? So we do this again. To recap, we have convolutional neural network. So basically, well, in the literature, actually, this is sometimes called hourglass structure in the CV computer vision literature, and we'll see why. So okay, so original one is, let's say we have Nori voice WAV, okay, and Nori voice.wav will be compressed into integer matrix, okay. So convnet plus that codebooks things, right? So the codebooks, you have codebooks, okay, and this is represented as number of codebooks. In the example we just discussed, it's 10, okay, and then something like 256. This is also time steps, right? This is T, okay, and after that we apply convolutional neural network again, but this one you do upsampling. The convolution gets bigger and bigger as we have many layers, and then finally we get C. Details are not important. I'm just glossing over details, but 32K. Now we have new WAV file. And then when we train this tokenizer and detokenizer, we try to make this convolutional neural network, train the convolutional neural networks and codebooks so that we can reconstruct the original WAV file as accurately as possible. So the example we showed was Nori voice reconstruct the WAV, and these WAV files should be as close as possible, right? Should be similar. This is the training process. In inference, of course, we just use before we train, we use this part, encoding part, to tokenize to get discrete tokens. So this is the part we use for pre-processing. And then for inference, the output is these integer matrix. So we need to use this part to get the output WAV file. So this is inference. Okay, so this is how audio tokenization works in a nutshell. Let me know if you have further questions. All right, thank you.